theme today is electrification forest operations is no longer a distant concept. So it's becoming a more real application. So we see every day new trials, new applications coming, becoming reality under trials. So it's something that will be part of our forestry business, of our lives more and more. So that's what we expect. That's why this event is relevant. We know that still a lot of questions about the challenge and the opportunities, so that we decided to promote this event to shed a light on this topic. So with that, we expected to share with all participants potential applications on the electrification, what are the challenges, opportunities, and what is the current status and potential future trends. And as we have done in the previous events, so it's a mix of academia and industry. So it's a good mix that we can share experience and have a combination of these two groups. So I would like also to encourage everyone to participate actively. So please share your questions and you can post in the chat at any time. And we will have the presentations, 20 minutes presentation, and then 10 minutes question and answers. So that's the plan for today. And just before we move to the first presentation, I would like just to give a quick comment about IUFRO. So this event is under IUFRO. And for those that may not know what is IUFRO, is an International Union of Forest Research Organization. It's a non-profit, non-governmental institution that aims to promote the generation, exchange, and dissemination of research in forestry. So through its numbers, voluntary work across the world, IUFRO has representative in several areas by divisions, unit groups, and this event is being organized by IUFRO, as I said. So it's a voluntary work to promote this collaboration between research, industry, across the world. It's based in Vienna, Austria, is the headquarters of IUFRO. So thank you once again, everyone, for attending this session. And then I will move to Bruno. Bruno, please help to introduce the first speaker.
Okay, Angelo, thank you. And hello, everyone. First of all, I need to introduce myself. My name is Bruno Schettini. I am a professor here at the Universidade Federal de Viçosa in Brazil. I work with forest harvesting and ergonomics things in forest workers. Me and Professor Arthur, we share our department. We basically work with forest harvesting, forest transportation, forest roads, and ergonomics. So first, our first speaker is Dr. Anna. Anna, first, thank you for your time to be here with us. Anna is a senior researcher from Stockford Swedish Forestry Research Institute and the Royal Institute of Technology. Anna has more than 20 years of experience for transportation research and innovation, and is currently leading the project Transition to Efficient Electrified Forest Transportation. The project aims to accelerate the transition to electrified trucks and engage 23 partners. Anna, you have 13 minutes to your presentation, so thank you for your time and go ahead. I think you need to open your microphone, Anna.
Okay, we try now. Good.
Yeah,
so
good.
Thank you very much. Thank you for your introduction and thank you for having me here. It's super fun to be here. As Bruno said, my background is from transportation and not from forestry, but I think forestry transportation is a very exciting area. So I will present, today how we are working on accelerating electrification of heavy road freight transport in Swedish forestry. And we know that we need to decarbonize road freight transport to meet climate goals. We know that electrification will be a key. We know that in order to reach the climate goals, we need to have 50% of new sold trucks to be electric by 2030. And we know that in Sweden, it was 3% in 2023. In Europe, around 2% all over the place. China is leading, but I think Europe is kind of second place here. So that means that it's even lower values in the rest of the world. So the question for us that we are addressing is, how can we speed up this transition? We're working with the road sector, and we're doing collaboration projects with the forestry industry. Before we go into the projects, I just want to highlight a few things about the Swedish forestry sector, which is good to keep in mind when we're talking here. So we are working. This is a map of Sweden, and we're the forestry sector's transports are distributed all over the country. In contrast to, I would say, other freight transport in Sweden, which is mainly along one or two main roads that go through the whole country. We know that nearly 20% of all road freight transport in Sweden is the forestry sector. We have an average transport distance of around 90 kilometers from the forest to the industries. We have an average gross vehicle weight of about 70 to 74 tons. So they're relatively large vehicles driving. And the emissions from the forest, from the transport, comprise are 50% of the sector's transports. So it's a significant amount of CO2 emissions that comes from transport in Sweden in the sector, and it's 30% of the cost. So we need to do this transition also cost efficient. The sector altogether has set up the goal to be fossil free by 2040, and they are serious with this goal. Is my impression from meeting the industry. One can ask, isn't it challenging to do electrification in the forestry sector? This is actually an electric truck with a crane driving. By now, it's out there operating. But we think that if we can make it here, we can make it everywhere. So the first question is then, is it feasible to electrify forestry transport? Those are results from a simulation study that I've done together with my colleagues, where we have developed a fleet planning tool that takes a lot of inputs here. The transport demand, the share of electric trucks in the fleet, vehicle specifications, charging networks, etc., into a fleet planning tool, which we call elroute, which is electric routing in Swedish. And it basically finds for a certain fleet with a specific share of electric trucks, it finds the optimal routes. And this simulation tool, it's using detailed road data, detailed energy consumption models. So it is quite realistic. And we have seen from our previous studies that energy consumption varies a lot depending on the road the trucks are driving on, and not only the road surface, but also like how much acceleration, the decelerations, etc., how many crossings they go through. So it's all relies on detailed data, but of course we do not have the data from the electric trucks. So there we need to use the data from diesel trucks and recalculate it and also take into account energy regeneration while braking, etc. And when we have studied the results, I just wanted to give you a few examples here. We have analyzed transport data from 4 different cases using this tool spread out over the country, and I stress this spread over the country a lot because the conditions are very different from being in south of Sweden compared to being in the north of Sweden, both climate, but also transport distances, and also actually the business context differs between different parts of the country. So we have used the tool to analyze data from 5 different cases, real transport cases, and we have a preprint of a publication out there, so you can read more about the details. But just to highlight some of the findings, is that we found that already today, around 60 to 80% of the transport work can be electrified if we assume like technology development that is like the best you can buy from a truck shop today, and with about the charging network that could be present around now. So I think that's like it's interesting to see that already today with today's technology we can do quite a lot. We have run several different types of scenario analysis varying different parameters. We learned that with a larger battery, we can of course electrify more, but that is only valid up to 700 kilowatt hour battery size. Going bigger for the batteries doesn't help because we need to stop and charge anyway. So, and or we need to stop. Yeah, we need to stop anyway due to the driving legislations that we have in Europe, that you're only allowed to drive for 4.5 hours, and then it's a mandatory rest of 45 minutes until you can continue and drive 4.5 hours again. So oversizing is not a good idea. There are more different simulations in the preprint of the paper, and hopefully soon also in the paper, which I'm super happy to share with you if you are interested. But we have also run simulations where we have looked at potential future scenarios and varied several parameters at the same time. And then we see that if we vary the diesel price, charging network, and battery size at the same time, and in a scenario that could potentially be mimics what we believe would be the present in 5 years from now, around 2030, we see that we have the graphs here tells us that we have around TCO parity between diesel and electric trucks, and also that it is possible to electrify nearly all the transports. The graphs here tells us also that with electric trucks, we will need more trucks compared to the diesel trucks. So the productivity of each single truck will be lower. So we need more trucks, but on the other hand, the operational costs for the battery electric trucks will be lower, so we still reach cost parity. So this all sounds good. We are happy and believe in this for the future. And we're not the only one that do that at Skogforsk as researchers. We have started a big collaboration project together with the partners from the industry. We call it TREE, Transition to Efficient Electrified Forestry Transport. And this is a project where we want to realize the results. We want to do this electrification for real. So three, we have the aim to remove system barriers with doing electrification. And the idea here, the background here is that technology is not the barrier, but there are so many other barriers related to business models, operational models, transport planning, charging infrastructure, etc., that are actually the barriers for realizing electrified forestry transport. The project, we cannot do this alone. We are 23 partners in the project from the whole value chain, the transport buyers, forestry companies, logistics service providers, charging companies, software suppliers, hardware suppliers, etc. So it's really a broad consortium. It's around 16 million euro project budget, plus the trucks, plus the charging. So 60 million euros does not include the trucks and the charging infrastructure, basically. In the project, we will operate 12 electric trucks. We will operate one electric trailer. One of the trucks is a high-capacity transport, 94-ton gross vehicle weight, electric, full electric, transporting wood chips. And we will also try mobile energy storage systems. This is how we see at the system. As you see, this picture is mostly to show you that we believe, electrification, it will have a chain reaction. It influences all part of the transport system, from, of course, electricity and charging, business models, logistics and planning, technical innovation, but also culture and behavior related to the drivers, but also behavior in all organizations involved, basically. So we address all those 6 different fields in the project. We are going to operate 12 electric trucks as of today. 11 of them are actually out there driving. Here are 8 of them on pictures, but half of them are wood chip trucks and half of them are timber trucks. And the timber trucks are equipped with their own crane, which is kind of the standard configuration in Sweden. I will continue a little bit here. I talked about this. 94 tons is the world's heaviest BEV. It's currently out there driving around, fully electric. And we know that since charging takes time from the driving, energy efficiency is even more important when we're going for the electric trucks compared to the diesel trucks. So therefore, we believe that 94 tons, like going up in gross vehicle weight, is one important key to make the transition efficient. So this truck can take 36% more load compared to a normal 74-ton truck. We are also trying other innovations, for example, an electric trailer, which we are currently doing tests on the test track with, to see how we can benefit from regeneration. The electric trailer can be used together with diesel trucks to hybridify them, but it can also be used as a range extender together with a battery electric truck. We also have these mobile energy storage systems. It's sometimes one challenge in Sweden is the not grid congestion, which is a problem in many other places. But especially for the forestry sector, it could be like grid connection at all. So then we think a mobile energy storage system, which is basically power bank for trucks, could be an alternative. We are also talking about developing digital fleet planning tools. We know that they are super important. They're critical. I don't have time now to go into the details of them, but we are doing that also. If you're interested in any of those parts, please feel free to contact me. We have also done some work about what the drivers think about driving the electric trucks. They typically think about charging, the business can be profitable, and flows and logistics. But we also know that those who have tried, they don't want to stop. They love the work environment. And we are also testing, I think my 20 minutes are kind of out. But I just want to highlight also that we are doing systems modeling, exploring how the different actors' goals and decisions will influence each other, and how we can speed up to understand what interventions on the whole system that we can do to speed up the transition. So with that, there are a lot to talk about here. Just to end this presentation is that, transition to electrified forestry transport, it is possible. We have learned that, and it is necessary. But it is indeed a complex system. So the only way to do it is to do it together. So that's it.
Okay, great, Anna. Thank you so much. Excellent presentation and quite interesting, innovative project. We have first question here from the chat is about if there are current available e-trucks in the market, such as Volvo, and what are the battery capacities if capable of hauling 65 tons and above. So if you could comment about existing off-the-shelf on the market trucks with capacity for 65 tons and above.
Yes, so all the trucks that we have in this project, which are 70 tons or more, they are commercial trucks that one can buy from Scania currently. So there are opportunities. I see new models released all the time, and they typically have right now, they have around 500 or even 750 kilowatt hours battery size, and typically charge with around 375 kilowatt charging. But I know that they are currently also testing megawatt charging with the new MCS standard for charging. So the trucks can charge up to 1 megawatt or even above that. So the development is going super fast. And I think we have still the trucks that we are using in the project. I mean, they were ordered 1.5 years ago or 2 years ago. So they are old in this sense, but they still work. So I think trucks that one order now, they can drive with 65 tons for 4.5 hours.
Okay, good. And those are the project is 12 units, right? That you presented.
12 trucks in the project. Yes.
So are not prototype. It's already market units, right?
Yeah, exactly.
Okay. Just one quick question from my side, and because this kind of technology, as you mentioned, depends on a lot of different variables that you need to balance to see if it's feasible or not. But what about the charging? This impacts a lot in the cycle time. We understand this is like a phone. Time to time, they are improving the battery capacity and reducing charging time, increasing capacity. But what is the driving from the industry? What have you heard from Scania? What their trends? Is improving the battery incrementally or time to time, or moving to a different technology like doing swap of the batteries? Do you have any? What's your perspective on that?
Yeah, so my really not Scania. Since I'm an
just idea, just your trend you could see during the project.
Personal ideas. I think. What we see now is kind of more incremental improvement of the battery. I expect new battery technologies to come, and I think I read about that, but I'm not a battery expert, so I don't know the time to market for them, for the new batteries. I think we also see development of chargers. I would say that currently the main barrier is speed of charging. And that is mostly not the truck. The truck can take relatively high power, but it's more the chargers and the electricity, the supply, like the grid that connects the charger, that has limitations on the power that they can deliver. So charging time is, I would say, one of the main barriers now for having high productivity. Because as I said, I mean, a larger battery, for at least as long as we live with this 4.5 constraint of driving time, it's not necessary to have a bigger battery than what you need to drive for 4.5 hours. If you then imagine that you can come back and charge it during the lunchtime, which I think most, but if we have that hypothesis, it's not necessary to have a larger battery, and that's what we saw in the simulations also. Over 700 kilowatt hours battery doesn't help, but faster charging time helps, because you need to charge within the mandatory lunch break. So I think that's where, but then of course, also, especially in the trucking industry, where we have the weight constraints. So a bigger battery means less wood on the vehicle. So from that sense, yes, it's important to work with like a higher energy density in the batteries. But right now we believe that charging power and charging time are the most important factors to work with.
Okay, good. Thank you. There's another question, Anna, here from the chat, from Gustavo Torres. What is the operational cost per kilometer of the electric truck compared to a diesel equivalent? Maybe in a percentage of the diesel cost. If you compare maybe TCO,
I will not go into that right now, because it is very sensitive to the diesel price.
Okay.
So I'm happy to continue the dialogue with you, Gustavo. To talk about it, and we do have some work done on that and analysis, but we have realized that it's very sensitive to especially the diesel price.
Yeah. Okay. Yeah, and basically from what I've studied and heard, and correct me if I'm wrong, usually the capex is something that is still higher, but in the opex you can have a saving in the electricity, especially if you have some different, depending on the source of energy, if connected to a pulp mill, for example. But this is very sensitive, as I said, depends a lot on the situation.
Yeah, exactly. But we should also keep in mind the capex is higher for the electric truck compared to the diesel truck. But since we are working with the forestry trucks, the trucks here, they are quite complex. So the truck cost of the whole vehicle cost is relatively smaller compared to a standard long haulage truck that only goes with standard like container trailers or whatever. So the actual influence, I don't remember the numbers in my head right now, but we have them in one of our papers, that we realized that even if the capex of the truck is much higher, the capex of the whole vehicle is not that much higher.
Okay, got it. Okay, so maybe, Rochelle, we could discuss this topic for hours. It's very interesting. It's a lot of points. maybe we can go to the last question because of the time. We have a question here from Raul Lyer. How did the electric trucks perform in extremely harsh winter conditions when temperatures would go below minus 25 degrees Celsius? How did the drivers navigate those challenges?
Yeah, I think the main challenge is actually not the temperature. Of course, that increases the energy consumption. But what is even more challenging is the increased energy consumption from like snow and muddy roads, and for the big 94-ton truck that vehicle has many wheels. So if it's raining or like tough road surface conditions, that is a larger problem if we're talking about energy consumption compared to actually the lower temperatures, because the trucks are equipped with battery management systems that keep the batteries at the right size. I guess that's the main, and that's why it's so important with the energy consumption models. For the planning, we need to know the transport planning becomes more important because we need to know the exact energy consumption.
Okay, good. Sorry, there was the second part of the question that from Raul also connect to question from Octavius about the driver's experience, what they say about this technology.
Yeah, they really experience that it's like they are less tired when they come home from work. It's less sound, less vibrations, etc. There is, of course, so overall they really like and appreciate the driver's environment. There is, of course, some kind of like range anxiety, especially in the beginning. But that doesn't seem to be so pronounced by the drivers. And one challenge is, of course, that they think about whether, is it not profitable to drive with electric trucks? Are they too expensive? Because many of the haulage companies in Sweden are kind of family-owned companies, etc. So they are aware of that. So that is a bit on the stress side, but like driving experience, they appreciate it very much.
Okay,
and
great.
That we learn. After driving a couple of weeks in the electric truck, they know how far on battery state of charge they can go, and so.
Okay, yeah, they start to get used with the technology and how to get the best of that.
Yeah.
Okay, great. Thank you so much. And there already have some additional questions in the chat, but because of the time, we move forward. And then please, if you stay with us, you feel free if you want to comment something else in the chat or any question, if you want willing to answer. Thank you so much once again for your time and for sharing your experience with us. Very, very, very good. Thank you. So
Thank
now,
you.
Bruno can introduce the next speaker, please.
Angelo, I think we need to change our schedule.
Yeah. The next from Michael and Professor Hunt.
Michael and Professor Hunt, thank you for your time to be here with us. So Michael is the Director of Sales and Marketing for Airburn's. So Michael worked in sales over the past 24 years, brought many opportunities to expand Michael's knowledge in different industries. And Dr. Hunt is Professor and Director of Forest Operation and Biomass Utilization at Ecological Restoration Institute from the Northern Arizona University. So Michael and Dr. Hunt, please go ahead with the presentation. We have 10 minutes too.
Okay, perfect. Thank you so much. Again, my name is Michael Schmidt with Airburners. Is my presentation showing at this time?
Yes, it's okay, Michael.
Yeah, it's okay.
Okay, perfect. Well, I think from Anna's presentation, this is a great next step into the industry. So again, I work for a company called Air Burners. We've been in business for a little over 30 years now. And with that, we manufacture machines that burn wood waste with little to no smoke to dispose of this wood waste. We're set up here in Florida, and we have thousands of machines all over the world. The presentation, the scene that you see here is not a representation of how many machines we have, but mostly where we sell the majority of our machines. So the United States, Australia, all over Africa, South America, but majority of our machines are here in North America. We're on every continent except for Antarctica. When it comes, what we're going to discuss today is the biocharger. So this is off-grid, creating electricity, putting this electricity into a battery storage module into the forests. And then the CharBoss, which is, this is a machine that automatically produces biochar. So the reason that we're looking at this is that vegetation seems to be a problem all over the world. So not only am I the director of sales here, but we have a sales team that they cover North America. I take care of international sales. So we're starting just starting doing a little education on social media, which has really opened up international questions about wood waste. And I'm finding that there is a problem everywhere, not only here in North America, but problems with wood waste, taking care of unwanted wood waste, whether it's invasive species or just wood waste that cannot be utilized because there's a large amount of it all over the world. So here in the United States, right, we're finding that there's a lot of recycled green wood waste, and these are wood waste that are being made into chips, and then these chips are used. However, many times they're just disposed inside of the landfills as cover, which is not good. But there's just so much wood waste that actually still goes into the landfills, creating methane, and then the emissions to get all of the wood waste there and filling up landfills. So this is just wood waste here for municipalities where homeowners put it on the street and then it's taken to the curb. This wood waste is not including wildfire mitigation or tree mortality. Just in the Sierra Nevada forest here in California, we have an additional 800 million tons of dead standing wood waste that were killed off by an invasive species. So there's millions and trillions of tons of wood waste just here in North America that has been killed off by an invasive species that there's no valuable part to the market. So and then the agricultural industry is really big in California. They switched to start utilizing our machines to dispose of wood waste, as we're known as the best available controlled technology, which simply just means environmentally, we are the cleanest way. The fireboxes and the air curtain burners are the cleanest way to dispose of wood waste, and then also the least expensive way to dispose of wood waste. So we're just talking about tree mortality, so it's a major issue. So how do we eliminate our vegetation waste today? You can grind and haul it to a landfill, open burn it. This is a prime example of a grinder that's running. This was a test in Australia that they wanted to do. This was an opacity test for our machine. And so this was a Peterson Pacific grinding wood chips that just by chance were there. This was there the same day. And so once they stopped running the grinder, then you can see the air curtain burner running behind it. And that's the point of our machine, is that you're able to dispose of wood waste, turn it into a soil amendment, but dispose it in environmentally the cleanest way possible. So this is another grinder, running with making chips. But again, running a grinder, it takes 100 tons of wood waste or 1,000 tons of wood waste and makes it into 1,000 tons of chips. It simply just lowers the size of the material for transport, which is beneficial. And that's what the grinder was designed for many years ago. Open burning, it's very slow. So, if you open burn a stump, that can take 4 days, right? If you open burn, it creates a lot of particulate matter that goes up into the environment. So it's slow and smoky. This is an open burn that happened out there. It's just an amazing amount of particulate matter. And if you don't take care of the wood waste that's in the forest, in areas where you have spontaneous combustion happening because there's too many chips sitting in one location, you're going to get this problem as well. And so too much wood waste and not disposing of the wood waste, that's what we're looking at. This is another test that we did with Environment Canada on our machines. So this machine is going to get a little bit of this is a 327 looking at compared to open burning. So this is at the BC Hydro Dam where all of the wood waste would come up from the waterway and then it would clog the dam. So they used to open burn this material. And when they wanted to run a test with our machines, they put out 2 S327 fireboxes. Each firebox burns 10 tons an hour. And so they burn 20 tons of wood waste in 1 hour with our machine. And they burn 20 tons of wood waste over on the opposite side. This is that same picture. This was a helicopter view that they took. And you can see in 1 hour, there was little to no smoke with our machines. And in 48 hours, that was continuous particulate matter going into the valley, going into the mountains. I mean, just the fires from British Columbia are very far away in Canada from where we are in Florida. And we were still affected by the smoke here in Florida from the fires in British Columbia. So this smoke definitely does travel, but that was 48 hours of smoke, continuous smoke. So our machines, we eliminate the wood waste, we turn it into a soil amendment, biochar and ash. And then also we create electricity, which I think this is the biggest point of why we're here today. But I think you have to understand the firebox, because the firebox, this is what we sell mostly of right now. This is what keeps us in business. This is what allows us to grow every year, because so many people need to dispose of wood waste in the least expensive way possible. And the firebox, 10 plus years. This machine, but you can run it 10 plus years and you minimum maintenance on the machine. Really, the only maintenance is the diesel engine or the electric motor. So in this box here that you see to the right, you have a diesel engine or electric motor. It powers a fan. The fan blows air through the manifold over top of the firebox. This air curtain, once you start the fire up in the firebox, you turn on the air curtain. And what this will do is that when the machine's fully up to speed and running and the air is coming out of the manifold, it creates an air lid over top of the firebox. This lid traps the particles of smoke under the air curtain for fractions of a second, causing them to reburn. The secondary burn reduces the smoke particle size so small, it generally looks like heat waves coming out of the firebox. The whole purpose of the air curtain is to create this secondary burn. The extra air also helps to oxygenate the fire to burn as fast as possible. So as I mentioned before, if you were to open burn a stump, that can take a few days. Inside of the firebox, it'll burn up in just a few hours. We're here in the United States, we're one of only 40 companies that were tested by EPA. EPA tested our machines here in the United States. EPA in Australia has tested our machines, but we are a CRADA partner with EPA here in the United States. We are a current CRADA partner with the U.S. Forest Service. And the CRADA agreement with the U.S. Forest Service, they came to us and said, we want a machine that automatically produces biochar. And we'll talk about that in just another moment. But the Department of Defense, just about every military base across the world has one of our machines, Department of Energy. And then, of course, USDA, they own our machines. And then they promote our machines here in the United States about creating the ash and biochar. The different sizes of the fireboxes are, and the fireboxes, just to preface this, the fireboxes are going to be part of the biocharger we're going to talk about in a moment. So I want you to take an idea of the sizes. You have a 300 series size, a 200 series size, and a 100 series size. The biocharger is set up for the 200 series size. But Once you go to a 300 foot or 300 series size, the firebox, it gets a foot taller and another foot wider. When you go down to a 100 series size, it's another foot shorter and another foot less wide than a 200 series firebox. The last two digits give you the interior size of the firebox that you're burning in. The 100 series size fits in a Connex container. We ship a lot of 100 series all over the nation because it's very inexpensive to ship. The Boss series is our burn boss. This was designed for the U.S. Forest Service to burn and take care of disposal and do wildfire mitigation out in the forest, and then also in the ag industry. This is utilized with farmers who want to make biochar. We have a track boss, which is like our standard burn boss. Again, our standard fireboxes have an open floor, so you burn right on the dirt, right on the ground. So the track boss has an open floor where you burn right on the dirt, right on the ground. And then this has a remote control, so you can move it around in the woods. As one customer with 3 burn bosses wanted one track boss. The char boss that you see on the bottom, this is the one that the U.S. Forest Service came to us and said, hey, we would like a machine that automatically produces biochar. So the burn boss morphed into the char boss. The char boss has 2 thermal ceramic panels inside of the firebox that will move, dropping the biochar onto a conveyor belt system. This conveyor belt system takes the biochar out of the char boss, drops it into a water pan, locking it into the biochar state. This machine can produce up to about 500 pounds of biochar per hour. Average is probably going to be more around 350 pounds per hour, burning around 1,500 or processing around 1,500 pounds to 2,000 pounds an hour in the unit itself. And you'll use about 12 gallons of water per hour running this machine, up to about a 30% biochar conversion. So I have many documents and many tests on this, so we can go into it in much more detail in the future. And then the next machine that I like to talk about is the biocharger. These machines are both newer to the market. The biocharger, this one wasn't feasible due to batteries were too expensive. Now Rolls-Royce, we were able to purchase a battery from Rolls-Royce. So working with Rolls-Royce and Volvo Construction, we were able to produce this machine. This machine is an off-grid power producing machine that you can put your wood waste that's not being used, your slash, your stumps that you don't have marketable material for, put it into the biocharger and create electricity. So dispose of your wood waste, create biochar, create ash, and create electricity. This is a complete portable piece of equipment. So unlike the past structures where this was your typical biomass incinerator that would go and incinerate chips and then it would create electricity, this was too expensive. The emissions were too high. You had to transport. You had to grind the material twice. A lot of hauling, a lot of emissions, many emissions. And then once it gets to the biomass facility, you took a complete burnable piece of material into a material that doesn't burn. They had to use a supplemental fuel of gas or diesel to burn the chips, all to create electricity. Now, our machine, portable, takes 6 hours to set up, 6 hours to take down. You have your material, your stumps, your logs, your branches, your slash, anything that's not marketable, burn it inside of the firebox, dispose of it in the firebox, make biochar, make ash, make electricity. Once you're done using it, you can move it to the next location. My recommendation, keeping it in an area for at least 6 months, give or take. Battery-powered machines, this is the cart and the horse. Which one's coming first? And the battery-powered machines are now hitting the market. We're seeing them all over here in the United States. We're currently using one. You see the L25 down in the bottom left-hand corner, the Volvo. We at our biocharger site, we have a biocharger right down the street site where we manufacture here at one of our customers' locations, and we're using the Volvo wheel loader to load the biocharger. So it's a great piece of equipment. So here's some of Volvo's electric equipment there. And you have your grid connection that's out there, your portable power, and now your on-site generation with a biocharger. What is it and how does it work? You have 4 pieces. You have a firebox module, a cooling module, a power module, and a battery storage module. So again, this is off-grid, not connected to the grid. With this, you're going to dispose of the wood waste inside of the standard firebox. With this standard firebox, you're going to dispose of the wood waste at 3 tons an hour, 5 tons an hour, 7 tons an hour, 8 tons an hour, 10 tons an hour, depending on what size firebox you want, or depending on how much wood waste you believe you need to dispose of. The power module sits over top of the firebox. It's not connected. It just sits next to it. It'll take the heat when it needs the heat. When it doesn't need the heat, it won't take the heat. But as that heat comes in, it heats up a working fluid. That working fluid will expand, creating pressure. That pressure turns the screws inside of the ORC system, the organic Rankine cycle system. That's the part that makes the electricity. The organic Rankine cycle system will take that electricity and then put it into the battery storage module. The battery storage module that's built by Rolls-Royce is currently a 600 kilowatt hour battery storage module. So this battery storage module will hold on to the electricity. That working fluid that was just heated up will then go into the cooling module. The cooling module will cool down the working fluid, and then the working fluid will be reintroduced back into the power module. This entire system is worked off of a red button and a green button. So it is an automated system. The end user just needs to add wood waste into the firebox module to keep the heat going. So when the power module needs heat, it'll grab the heat automatically. This is a system being set up out in California. One county, Kern County, they purchased 3 systems. They have 2 PG fireboxes and they have 1 biocharger. The only difference is one is on grid, the other one is off grid. The PG firebox, that's the one that's on grid, so it does not have a battery storage module. The PG firebox, this is connected to the grid. The ORC system that we currently have is a 100 kilowatt ORC system, but coming out in 2026, I believe our engineers are working on a 350 kilowatt system. So now this basically means a bigger battery and a bigger ORC, more electricity. The PG firebox hit the market about 8 years ago. So this was something that we thought about 25 years. We wanted to build, the president of our company, head of engineering, wanted to build this system, but it took a while to actually hit the market and become feasible. So again, the PG firebox is on grid, the biocharger is off grid. So the variable, this is the cooling module. So all of our machines are portable. They're designed to be drug around, so you can move from one location to the next. The battery storage module, you can get this customized with your electric outlets, so you can recharge your cell phones, recharge chainsaws, plug in your microwave to cook your food or an oven, but then more importantly, recharge your electric vehicles. I know that when Anna was talking about that charging was very important, Volvo has a slow charge, which is about a 4-hour, I want to say it's a 4-hour charge, so it's more like overnight. And then they have a high voltage charge where you can charge within 30 minutes. So that is newer technology, but I know it's available through this type of system. Again, we've worked with Rolls-Royce and Volvo to really develop this system, and that's how the biocharger was sent. And so yes, we can definitely share this presentation, and I'll be more than happy to give this presentation and share it with whoever would need this. So this is daytime operations. You go, you dispose your wood waste. You know, this system also has 1 megawatt of thermal energy. So if you wanted to set up a kiln out into the forest and dry the wood waste and cut the wood waste and ship the wood waste out of the forest, you have 1 megawatt of thermal energy that you can utilize from this system as well. But then more importantly, charge your electric vehicles out in the system. This is at nighttime. So if you're running all day long, you can also charge your equipment at night. So you can charge your equipment during the day, charge your equipment at night. This system will continuously just charge. So I thank you so much. I'm going to introduce Dr. Han to talk about how this system can be utilized in the industry in itself. Here's my contact information. Be more than happy to talk again in the future. Thank you for having me.
All right. Thank you, Michael. And hello, everybody. Everyone, I'm from Arizona. So yeah, I'm working in the university, but I've been working. I'm doing the research on the chop-offs, air curtain burner, and the bomb boss, and I also looked at the biocharger about the 2 years ago. Yeah, it was April 24. So last year, I guess, in California, they were the biocharger was set up, you know, the landfill area, near landfill area, and then instead of putting all the organic waste into the landfill area, they actually burning it using disposing it using a biocharger system, and then create the electricity. So they were able to save a lot of their landfill space by doing that. And further, they were producing the electricity to run the equipment running, and they're being operated in the landfill area. Now, the reason I'm interested in this system because you know, we all working in the forestry, but and then we you know, work with a lot of things related to the forest management, active forest management, which generate large amount of logging slash. And we've been having a very, very hard time to manage those logging residues because we don't have a biomass power plant nearby. And as the Michael suggested, they indicated that the open burning create a lot of particle matters going to the air, and a lot of smoke goes to the air. So they're very heavily negatively impacting on air quality. So we've been looking for a different solution to manage the biomass. So we found that this air curtain burner systems, they are burning very, they efficiently and with the clean, and they also have one of the good things about they're controlling embers. So embers is not flying far away. So you can safely burn running the system year round, which is wonderful. So we found that this air curtain burner, the biocharger, bomb boss, chop boss, all those tools we found very handy and very effective, and we would love to use them for managing our biomass waste. I do know that this system does not solve all the biomass waste we have. Because the area I worked in the past about Arizona, the California and Arizona, you're looking at generating the logging slash 20 to 40 ton per acre. So that translated to about 40 to 80 tons per hectare. So it's so much volume, and then you're cutting, with the typical ground-based mechanized logging system here in the Western United States. You're looking at about 20 to 30 hectares per acre with the one system. So you're talking about quite of the volume being generated from the logging operation. However, this system, however, now I'm really getting excited about this electrified, operation, because we can burn those waste material on site, and then we can charge fellable skidder order on site, and the next morning is ready for operate. So that's a very exciting idea to think about. So I think as we all know about we have we need to advance more technologies about reducing the amount of time for recharging and the cost of the battery. We still have the concerns about horsepower. So we still have something more to do with all the other technologies to be developed, advanced. But I think we're on the right direction, and I'm really excited about all the electrified technology ideas, along with managing our organic biomass waste. I think that's a really good, wonderful, combination, compatibility right there. So with that, I think I appreciate the air curtain burner advancing those kind of technology and ideas, and I hope we can see more advancement, and so we use that technology for managing our organic biomass waste. With that, I'm going to send it back to you, Angelo. So see if we can take any the questions of Michael, and I also available for answering my questions.
Great. Thanks so much, Michael, for very interesting presentation, sharing your developments, products, and Professor Hunt to bring your testimony here, your contributions, your experience on running this. And this is quite exciting because it's not only like talking about something technical, but I see this as the best word is a solution. So we may think on the several developments on new machines, trucks, and always there will be this kind of roadblock about charging, about electricity, and off the grid locations. So I think this technology is quite interesting to hear. That's not a prototype. It's not something new, but it's a long-term development, something proven that can unlock new technologies to be applied in the forestry. So it's very nice to hear that. And maybe not everyone knows or hear this before. As in my case, when I first met, we heard from you, Professor Han, about the technology. So it's quite interesting to spread the news and the spread on the technology, and hopefully we can see more on that on and on. First question here is from Octavius. He asked, can we use municipal waste too?
Well, I'm sorry, what type of waste?
Can we use municipal waste?
Municipal waste. So
Yeah.
no, unfortunately, these machines are only, great question, by the way, but these machines are only good for larger wood waste. So clean wood waste, stumps, trees, logs, branches, 2x4s, pallets. So no pressure treated wood, painted wood. There are many countries across the world that use trash and MSW for these types of machines. But for the most part, it's like here in the United States and under EP regulations, you're only legally allowed to burn clean wood waste inside of the machines. So, and it also cannot burn chips or grass or dirt. Those things just do not burn well. So pretty much anything that you're looking to burn in a campfire, you can utilize in our machines.
Okay,
but
great.
Michael, so we can still burn the trimmings, wood trimmings at the gardening waste. We can still burn all that green waste, not waste with the wood waste with the paint on it, all that kind of stuff. So those are not allowed because of the pollution issue. But using the air curtain burner, we can burn the green waste, the municipal green waste.
Yes,
Okay.
green waste. Thank you,
Okay,
Dr. Han.
great. Okay, maybe from parks, from like cleaning the arboristic side of the of the cities. Okay, but just to add another question here, just to clarify, to confirm, Michael, the understanding. So you mentioned it's only wood, plain wood, but no need, like as you shared some examples running together with a Peterson Pacific chipper. So there's no need to chip. You can use like a raw material, but with minimal cleanness based on industry standards, right?
Yes, yes. No need to chip and put chips in there. If you ran it through a chipper, you spent too much, right? So the chippers, grinders, grinders 1 million, 1.5 million, 1.8 million for a grinder. That's the same cost of this system. This system right now is going to be right around 1.8, 1.9 million US dollars, right? For the biocharger. Our standard firebox that goes with this machine, right? They're going to run anywhere from around 120 to 240,000 US dollars. But the whole biochar system that creates electricity can get for the same price for around a grinder, same price as a grinder.
Okay, and minimally clean wood, right? Like industry standards.
Yes.
Okay, good. There's another question here. It's about operational cost. What is about feasibility of operating cost? Can you comment about that?
Yes, we haven't looked into I don't have a feasibility study on the biocharger yet, but the operational cost of the standard firebox is less than $1 per ton operational cost. So less than $1 per ton to dispose of wood waste inside of the firebox. So going back to what I was mentioning earlier, here in the United States, many states that we're in, you have to be the BACT, the best available control technology, which means environmentally we'll have the least expensive, it'll be the cleanest way, looking at the SOx, the NOx, the PM 2.5, the VOCs, the carbon. So compared to grinding and hauling, compared to composting, and of course, compared to open burning, our machines will be environmentally the cleanest way to dispose of the wood waste, and then also the least expensive way. So will be the least expensive way as well. And again, operational cost less than $1 per ton with the standard firebox.
Okay, great. Another question, what is the moisture content the waste can have?
So when you saw that on the power, great question, another great question. You saw the PowerPoint presentation and you saw the BC Hydro Dam where they were running the two S327 fireboxes. We were pulling wood waste right out of the river, right? So it does not need to be dried out. They had to dry out on the open burn pile, I think over 4 weeks before they could burn the wood waste. Our machines, you can knock down the tree and have that green tree and burn it that same time. 65% of our sales currently go to landscape companies, tree companies, municipalities, landfills, people just trying to dispose of wood waste in the least expensive way possible. And then you have about 35% of our sales go to land clearing companies. So they're out there knocking down trees, and they'll take the trees, the logs that they can sell, and they'll sell the logs, and they're left with the treetops, the slashes, the stumps, and they'll take the slash and the stumps, and then they'll burn that material inside of the box, the material that they cannot sell. So it can be a high moisture content, very high moisture content in our machines.
So I just want to add one more thing there. So based on my own studies I did in the past with the air curtain burner, we looked at the thermometer to measure the temperature while it was burning in the box. We looked at very often about 1,000 to 1,200 the Fahrenheit, Celsius degree in Celsius. And with that idea, I think we were able to burn just a fresh cut whole tree fresh cut whole tree, we put it into the box, and yeah, but there was moisture content was not a really big factor because it burns so hot.
Oh, interesting. So you didn't have any experience of decreasing too much the calorific power because of the moisture content, and then like ups and down on the temperature. So it was relatively stable, right?
Well, I think what I saw, remember so yeah, this is that the organic Rankine cycle. They're taking the heat from the box to generate electricity. They're taking so little out of it, so they're producing more than enough heat to maintain the constant level of the production of electricity from the box, regardless of. I mean, obviously there's some changes as amount of the volume being burned in the box, but I think that there's always producing more than enough heat to produce a constant level of the electricity.
Okay.
Dr. Han
Thanks.
said it correctly. Yes, exactly. So there's a hood that expands and contracts over top of the box when the ORC needs more heat and less heat. And that hood will only stay over the box for about 2 minutes, and then it'll retract for about 4 minutes. So even if it needed more heat, it'll just get more heat. But if you're burning high moisture content material, it would still produce enough heat. But as long as it's a wood waste, you need that carbon. You need something that's going to burn well, which is why we were saying you can't burn MSW trash, right? So it doesn't burn trash. You need a good wood material, the stumps, the logs, the branches, the 2x4s, the pallets, vineyards. They even burn well with tomato vines. So there's a lot of our customers have been utilizing our machines for those for years.
Oh, great. So sorry, I just didn't get when you say that the operation is stable. Is because of the unit is very efficient on the burning process to keep the temperature, or is it because there is some sensor that can adjust depending on the moisture content, increase the fan speed or something like that automatically? Is there any sensor to adjust according to the process, or just because of the unit's really efficient, really efficient?
It's the way that the firebox is designed. Right, and that air curtain that flows over top, and it really any material that will burn, it burns much better in this system and processes it down into biochar and ash. But inside of the box, it'll burn around 1800 degrees Fahrenheit, and the air curtain, its job is to keep the heat inside of the box. The small amount of heat that will escape over on the hood side of where the power module is for the biocharger, right? So the heat is coming out in one specific area, but majority of that heat is kept inside of the box to make sure that whatever is being processed inside of the firebox, that it's processed in the most efficient way possible.
Okay, great. We have 2 additional questions here, even more. It's about the business model from your company, Michael. Are you selling only, or do you have rental model? Have rental for those units?
So we have dealers here inside of the United States and then we have private individuals that purchase our machines and also rent them out. But that's going to be here in North America. There are only 2 biochargers currently. Right, as the biocharger came out in 2025. So there's 2 biochargers that we have out on the market right now that exist. So that there's not a rental option for this at this time, unless somebody is going to purchase a machine and rent one. But it is we do have multiple rentals here in North America of just the standard fireboxes.
Okay, but not directly. Yeah. Okay. This from Nest City, before from moisture content was from Martin, England. And now I have a question from Juan Andrade. What is the recommended maintenance interval for the firebox? Or what is the time until a stop is required for residue cleaning?
Great question. So the firebox itself, the fireboxes are utilized many times over for disasters, right? So you have hurricanes and storms that roll through, and then there's blockages of rivers and you name it. So the fireboxes are utilized in disasters, and they will run them basically 24/7. You know, of course, you have to stop to refuel the diesel engine, but at that point, you stop to refuel the diesel engine. They'll utilize an excavator or ash rake to rake out some ash and biochar to clear it, because again, there's a 97% reduction, 96% reduction inside of the machine. So you'll have that ash and biochar that you want to pull out of the box, leave about 8 inches of hot embers, the biochar, hot embers inside of the firebox, reload the firebox with the wood waste. The fire will automatically start up, and then it's small loads more often. But there's really no maintenance on the firebox itself. I mean, California parks, they've been running our fireboxes for the past 20 years. Our thermal ceramic panels, that's Airburner's secret to our success. And their thermal ceramic panels for Cal Parks, which is California Parks, they transport the fireboxes all over California. Again, they're over 20 years old currently. And they did replace an engine. So they had to upgrade a tier 3 engine to a tier 4 engine as CARB, California Air Recycle, or that they look at emissions there in California. They made them replace the engine. But long story short is that you can run the firebox day in and day out, month after month, year after year, with little to no maintenance. The only maintenance is going to be the diesel engine, greasing the fan, but the box itself is built well.
Okay, excellent. I think that was the last question. Thank you so much once again, Michael. Please, sorry, Hunt, do you want to add?
Yep. So I just want to make that I guess a disclaimer. That I'm working for the university here. I'm not working for the company, Cotton Bonner. So I just want to I'm not necessarily endorsing that the company trying to promote the company. That's not what I'm here for. But what I'm trying to say here in my message for this presentation is we need to work together to be able to manage the logging slash. We here in Arizona, we're trying to thin the forest to reduce the wildfire, and then improve the forest health. So we trying to actively manage our forest that currently is not really doing well. But we've been dealing with so much challenge with not being able to remove the biomass waste. So that is why we are struggling. And so we would really welcome any technology, any idea, any innovation that help manage the forest waste. That would help us significantly to move forward with the implementation of the larger scale of the forest restoration and thinning operations. So that's my motivation for this kind of the project. So.
Okay, great. Thank you, Han. So no more questions. So I'd like to thank you once again, Michael. Thank you, Professor Han, for your contributions. It was very good topic to discuss. Very interesting. So before we move to the next, I would just like to highlight that Arthur has posted a link in the chat. It's about this meeting feedback. So please, if possible, please, I'd like you to take your time to, when possible, to fill this survey to give us the feedback on this event here and suggestions for the future events as well. So please, if possible, please help to share your thoughts on that. And then now, Arthur, can you introduce the next speaker?
Yeah, Angelo, thank you. Hello, everyone. Your feedback is very important. Yep. Please in our chat. Okay. Thank you for being here, and congratulations other speakers, Professor Zana, Han, and Michael. Thank you so much for your time. My name is Arthur Araújo, and I am professor in University of Viçosa, Brazil, in forest cutting, forest transportation, forest road, yeah. And I will be inviting our next speaker, okay? Um, Justin Harden, nice to meet you. Thank you for your time, okay? So Justin is Master of Science and Sustainable Energy Technology at the Technical University in Braunschweig. And master thesis focused on cell internal sensors in batteries. Science, September 2024, PhD student in the Department of Forest, Biomaterial and Technology of the Swedish University of Agricultural Science in the top area of energy supply for electrified forestry work sites. Excellent. Just in other times, he was research assistant in the group AI for batteries and the chair for electrochemical energy conversion and storage systems at the HN University, focusing on testing of sodium and lithium low batteries and development of charging protocols with the help of AI. Project assistant in the EU project design at local grid operator and energy supplier AW Heinlein, project management and energy planning for the decarbonization of the local community. So thank you for your time, Justin Herdingen. You have 20 minutes for your presentation. Okay? Thank you so much.
Thank you very much for the long introduction. I will more or less show a bit about my current PhD at the Swedish Agricultural University, and which is surrounding the electrification of forestry machines, so the machines which are doing the work on site. And for that, if they get electrified, the big question is also how do we get energy there, because in the forest there's not really infrastructure, and therefore we want to talk a bit and see a bit about how they could be supplied. Yes. So because electrification of forestry machines itself is a good thing and has a lot of benefits, and is currently catching on speed, because you have things like high torque and tractive force. We have benefits which you can avoid emissions. You can have the potential usage of renewable energy, and as well as you have big
Justin, you are mood, I think.
Okay.
Yeah, okay,
Now,
thank you.
when was I cut off?
I think it was you mentioned about avoid emissions.
Yeah.
Okay. Yeah. So apart from avoiding emissions, the second helpful thing is that you can save a lot of energy, depending on first studies and also other sectors. It's up to 70%, but still you need to supply quite a huge amount of energy to the work site, which is for a two-machine system like it's currently used mainly in Sweden, around 800 to 900 kilowatt hours per shift. Yes. But the thing is, we have a lot of those work sites in an area, and also we have renewable energy generation in that area. And in an ideal world, we more or less want to transfer that renewable energy towards the work site and then use it there. And for that, we need energy carriers, or like Anna said before, like mobile charging stations or mobile energy storages. In a decentralized system, like we see it in the picture, we have the production of those energy carriers in the region itself with the renewable energy. And then it's distributed from those production sites to the work sites where it's needed. But then you also have a centralized system like it's currently with diesel. So the energy carrier is produced in real big centralized locations and then only transported in the region to be distributed. We will look more or less over different energy carriers. So from the energy source, where the energy is coming from, how to produce the energy carrier, how to transport it, and also then how we can use it on site. But first, just a quick talk about the energy sources. Renewable energies are becoming now the backbone of a future energy system, and also therefore of a future supply system, because it became more and more competitive and is now, even without subsidies, more competitive or equal to a lot of fossil sources, and therefore very important. Another thing is biomass, which we are more or less in that sector, I think. But a big problem for biomass is that studies show the graph you see is for Europe. A lot of sectors are counting on biofuels and other usage of biomass to mitigate carbon emissions. But the problem is that current demand, which is predicted, probably won't be supplied by the available supply, which is why I think biomass and biofuels should more be reserved for sectors where there's really a lot of difficulties to electrify. And therefore we more or less focus now on electricity. Then let's start with a first energy carrier, which is hydrogen. You have more or less two main production pathways. The first one is electrolysis. So you use this electricity you generate it out of renewable energy and make hydrogen out of it. That is possible also in a decentralized way, because like in the picture you see, there exist also quite small production plants. The production itself has no direct emissions. Yes. Contrary to the one which is used mainly now with steam methane reforming, I think that's the main production pathway out of natural gas. But with carbon capture and storage, it can potentially be also become low carbon hydrogen, which is generated there. But due to upstream emissions, mainly out of natural gas mining, there's still a question mark if it really can be made low carbon. And as well, this is a centralized system then, because you need big production plants for that. Both of those are somehow already commercially available, but still need a lot of development, which is especially shown in the big price ranges you see as well. Another thing is the market situation currently. There is quite limited infrastructure for hydrogen itself, and there's also quite a big uncertainty how much it will be in the future. Like in the graph you see the big bar here, it's for global, and Sweden is planned infrastructure, production infrastructure till 2030. But this small amount is the financed one. So you see, till 2030, it's not that much of time, but there is a huge discrepancy, and you don't really know how much of the planned production will be really built, and if it can supply the future demand. Then, but further, let's go to transportation. I think the main way to transport it is compression. So you use the low pressure hydrogen out of the production plant, compress it into higher pressures. There are different systems like a 350 to 500 bar system and a 700 to 950 bar system. And there are also different tank types now, depending on cost and weight. Important thing is for us that also hydrogen is a dangerous good. So I think for most road transportation in the world, the ADR classification and the ADR rules apply. And for that, it's classified as flammable gas, and therefore also need to be handled accordingly, and you need maintenance and proper sensor systems. An interesting thing is below a certain level and volume which you transport, you only need to apply to lower requirements, which I call ADR light, or which a lot of people call ADR light. And for that hydrogen, the limit is 333 liters. The last thing is the usage on the work site. You can use it either in an engine or a fuel cell. Fuel cells are more efficient, but regarding usability on site, a hydrogen engine is a bit more has more protection regarding dust, or is not so much affected by cold weather, which is why for us, I think the hydrogen motor engine would probably be a better option. The second energy carrier is ammonia. Ammonia more or less is also a hydrogen carrier, so you generate it out of hydrogen together with nitrogen in the Haber-Bosch process. This is a complex and also intensive process, which is why it needs to be in a centralized system. Ammonia itself is pretty common in all over the world. I think in the US, they use it, farmers use it mainly for fertilization. Fertilizers are produced out of it, and which is why it's quite known how to handle it. And this is also why 80% of the hydrogen trade are also planned as ammonia, which is, shows quite the potential ammonia could have. The transportation itself is also done via compression, because at around 10 bars at room temperature, ammonia becomes liquid and therefore can be stored quite easily in normal steel tanks, but with ammonia-ready components, because ammonia is a corrosive gas and is also classified as that in ADR. Additionally, it's also a toxic gas, which is why it's important to have proper maintenance, and everyone which is handling it needs to be educated by it. And it has a quite low ADR limit of 50 kilograms. To use it on site, you have more or less two big main options currently, which is one, mobile crackers. So you crack the ammonium and get the hydrogen out of it, which you first put in there, and then you can use the hydrogen on site like I shown before. Or you use ammonia engines. Those are currently quite catching on in maritime operations. They currently, most of them need a bit of extra fuel, biofuel like hydrogen or diesel, to operate smoothly over the full range. But this can also be, the hydrogen, for example, can be generated out of the ammonia, which is why you don't need a separate tank or so with additional fuel. The third one, energy carrier I want to talk about, is e-diesel or e-hydrocarbons. It's more or less also a hydrogen carrier, like it's carbon hydrocarbons, and for that you need the carbon, as the name says. And to be really carbon neutral, the carbon needs to come out of the atmosphere. And for that, the main process is direct air capture, which captures the CO2 out of the air with electrical current and also thermal heat. And this is also the main bottleneck of the whole thing, because it's still quite in development, and also prices differ quite much, and there is also not a lot of trust because of that in the future market, as it seems right now, because from all announced Fischer-Tropsch production till 2030, it would only be enough to supply 1.6% of the jet fuel demand. And aviation is one of those sectors where electrification is really, really difficult. So this is one of the main application sources, and you see it doesn't really cover that in any way. And also only 2% of the planned hydrogen trade are hydrocarbons, which is also quite low compared to, for example, the 80% of ammonia I showed before. Which is why it's more or less the same thing like with the biofuel before. It should be reserved for sectors where it's more difficult to electrify, and therefore it shouldn't be the main solution. Which is why we also put that a bit in the background and focus on our last energy carrier, which is batteries. We have currently three different, these are more or less the main three commercial chemistry types, with NMC, LFP, and also now different sodium-ion battery chemistries are emerging. But it's also, there is quite a huge diversity there. Some have benefits in some areas, like LFP has high cycle life and also is the cheapest variant quite right now. NMC, on the other hand, has higher capacity, but they are it's also evolving quite a bit. Which is why the reason for that is there's a huge amount of funding in the development of batteries, and the improvements are really, really strong right now, because you have a mass market and also quite good in maturity. This is this can't be compared to any other energy carrier in this amount. For batteries itself, they are more or less a decentralized system, because you can charge them more or less at any bigger grid access point. Batteries itself are a quite safe technology, but also depends a bit on the chemistry you look at. But the safety improvements are ongoing constantly. Like on the video below, this is the new sodium-ion battery CATL showed, I think, earlier this year, and which shows no effect when sawed apart, even fully charged. So you see there is quite evolvement there. But still, it is classified as dangerous good, and also is relies on the ADR regulation. The usage on site is more or less, you discharge the battery again. Lithium-ion batteries are affected by cold weather, which is here in Sweden quite a big topic, which can reduce capacity and charging capabilities, and therefore you need a heating system. But there are also evolvements there, and for example, sodium-ion batteries currently are affected very low by temperatures, and are even operable till -40 degrees. So to summarize that more a bit, I want to compare some systems, how they could be used right now. We have LFP, a 350 bar hydrogen system, and a liquid ammonia system. And the first KPI I want to show you is the efficiency along the pathway. And there you see that batteries are quite efficient, because the losses from charging and discharging are quite low compared to all the production and conversion losses you have with hydrogen and liquid ammonia. But on the other hand, big important thing for transportation is the energy density, because it more or less defines a bit how much energy you can transport. And if you still remember that we had 800 to 900 megawatt hours should be delivered for one shift to the work site. Here you see 1 megawatt hour of energy, how much weight and volume it would represent. And there you see that batteries is quite heavy and also quite large in volume compared to the other two systems. But if you remember, we also have efficiencies which we need to think about, because if it's less efficient on site, you also have to transport more energy to the site, which is why if we add the on-site efficiency, we also have additional energy carrier which we need to transport, and then the batteries are nearly equal, at least regarding volume, to the hydrogen system. To summarize everything, like a bit of a ranking based on the literature I mainly found is batteries seem as the current best solution, mainly because of the efficiency, the maturity of the technology, and also the high safety. But hydrogen and ammonia could be interesting under certain conditions, especially if the production capacity, as I showed before, comes as planned and not as it's currently financed. You have bigger sites very far away where machines work quite long on there, then a high energy density could be needed, and then hydrogen and ammonia could be more interesting. And the third thing is that operators which work on the work site are ready to handle the safety related issues with ammonia and hydrogen. And the fourth thing with e-diesel, it's not really a viable solution, especially or mainly because of the limited production capacity. To round it up, I'm working in a research project which turns around electrification of forestry machines, and we are working together with Komatsu Forestry to more or less analyze that and evaluate that. And my work is mainly focused on the energy supply system, as I showed before. And my future and current work is to logistically and technically design this energy supply system and think about at which conditions which energy carrier would apply best. Yes, and that's my presentation. Yeah, I'm ready for questions, or as also after the presentation, you can always reach out if you have questions or want to talk about something.
Great. Thank you so much, Justin, for sharing your studies and your highlights and also your perception. So thank you so much for sharing. It was very interesting. Any question? I think in the chat we don't have a question yet, but let's chat a little bit in the end of this your presentation, and then we still have time for people if you want to put your question. Please help to put this in the chat. Just another information: we are close to the end, so we are 10 minutes before the end time that we planned. Unfortunately, we couldn't have a fourth presentation that was planned from Komatsu, so Komatsu team would share a concept prototype machine, a hybrid for water, but they could not join today because of some technical issues to connect. But we may plan a new event that we can bring more from the forestry machine sides to share as well. But so today we must finish on time. But before that, just let's explore a little bit on the Justin presentation experience. Justin, you mentioned in the beginning about planning. That is an important step, trying to combine renewable sources, and then you explore about what is the pros and cons or the best pathways. Can you elaborate about this planning? What did you use, any solution, or how would be your suggestion for some company that want to explore different sources of energy, of grid? How is the best way, how to start that, especially on planning?
Yes, I think I have to give the worst answer there is. It depends a lot on the conditions, because forestry itself is quite different in a lot of countries. For example, I'm from Germany. The distance from the forest to the infrastructure is not that long. We have somewhat normal climate, but then on the other hand, here in Sweden, you have this harvester and forwarder focused forestry with bigger work sites, and also quite far away from sometimes quite far away from infrastructure, and that all affects quite a lot which energy carrier is the best. Currently, for smaller work sites and also for smaller distances, it looks like batteries is the best solution for that. But it will depend quite a lot on the use case, and for that, I think there is a lot more research necessary to elaborate on that. But maybe for the machine itself, I think for that, the battery electric is quite a good solution, because then it's adaptable. Because you more or less have a lot of energy carriers, and maybe there is difference in availability in the countries, but in the end, you only need the electrical energy. So if the battery electric machines are working on the work site, they more or less can take every energy carrier there is to charge them. But if you more or less would focus on ammonia or a hydrogen fueled machine, then it becomes more difficult, because it can only take hydrogen or it can only take ammonia, and then narrow it down quite a bit regarding the energy carrier.
Okay. One more question I would like to ask you, if you could elaborate or give some perspective, because you have expertise on battery, on this kind of infrastructure, and this for the near future will be quite important, because, okay, we have maybe some power generation in one hand, the equipment in the other hand, but how to connect that? So, for example, from Michael from our burners, I understood that this easily can connect to the grid, to the net, or even like to a charging gun. But when we expand these kind of sources of energy, this can become more complex. So I believe, at least from my perspective, that companies that go in this maybe more complex scenario should look for companies like ABB or others specialize in how to connect, to plug things. Can you comment about that, Justin?
Yeah, more or less. The reason why I didn't go on that in much detail is, in the end, the charger and also the power electronics with this which comes with this charger is more or less always similar, and for that, I think there are quite a few companies, and especially regarding charging technology and charging infrastructure, I think a lot development is in there as well. Like also Anna mentioned, with higher charging power and all that. But obviously, it needs to be a mobile system, which then probably reduces the possibilities a bit more. Like I don't think like that megawatt charging is something which will be available soon in a mobile way, because you still need to also move the charging system. So that's why it's probably will go around maybe the 300 kilowatts or something as a maximum.
Okay, thank you so much. As you said, I think I just ask the audience if you have any questions, specific questions, feel free to reach out, Justin. Thank you once again, Justin. We are going to the end of our session today. Just a quick highlights and takeaways from to wrap up what we have discussed today. So as we mentioned in the beginning, so this is a technology that in the first moment looks that is something for the long term, very far away in the future. But what we have seen already a lot of things going on. So for example, logging trucks from Anna, we check that logging trucks, even though we also may believe that it's still like just delivery trucks for small loads in the cities is available, but we see that heavy duty is ready, already running, ongoing improvements, but this is really a trend. And the challenge is probably will be like a kind of gradual and incremental improvement in technology. So as many other technologies that we can see that sometimes people expect that to be perfect first moment, but this is not the way that innovation happens, not like overnight and then you have a perfect from 0 to 10. It's like many times it's like incremental. So that's we could see today that really the trucks is becoming a reality, heavy duty trucks, electric trucks. Biocharger, also very interesting to see that we can have solutions in remote areas. So something that can be like a very potential bottleneck becomes like starting having like these kind of solutions that can facilitate and unlock these solutions on terms of machines running based on electricity, and also solve the wood waste in the field. And lastly, sorry, this is very simple summary. I'm not trying to repeat everything that was said, but just to recap, also very interesting to see from Justin that we may have different energy pathways. And the planning is very important for sure, depending on the situation and the occasion. So that's all from our discussions today. I'd like to thank you, all the speakers and participants once again. Please, a reminder, please, for those that not yet filled the feedback survey, please access the link. We appreciate your help to give your feedback. And finally, on behalf of IUFRO, I would like to thank once again participants, co-moderators, and all the speakers. And please, let's keep the discussion ongoing and our ongoing research to be shared as much as possible. So thank you so much for attending, and hope to see you in the next IUFRO session. Thank you.
Good job there, Angelo. Thank you.
Thank you, guys. Thank you, Rohan.
Yeah.
Thank you. Hope to see you soon.
Yep.
Thank you, everyone. Thank you so much.
Thank you.
Thank you all.